So what we're trying to cover today, a little bit of background about suspended timber floors, the problems that we normally face, the interface between the void and the house and how that plays out, the risks that stem from that, the solutions that can be adopted to deal with those risks, a bit of insulation, a bit of ventilation of floor voids, and then look at various different measures that can be adapted, but mainly look at how and why the floor voids are actually important when it comes to retrofitting. First of all, floor voids or suspended timber floors are not that difficult to spot. You'd normally see a timber floor which will give you a very specific thud when you walk on this. You'll see brick vents on the outside. You might quite often see features like fireplaces and solid brick walls. They would normally indicate a high likelihood of there being a floor void underneath the floor. The floor voids are various. Predominantly, you see 4-inch joists resting on sleeper walls. These sleeper walls can be solid with gaps for services or honeycomb, or can be formed from pillars and cross supports. Most of the floors we see are honeycomb and solid dwarf. Now, what we find in the floor voids at the moment, in most cases, more than half, we find a ton of rubble. So these are not really accessible spaces. If you think about it, they're quite low to start with. And with rubble and cables and pipes and drains and mains and all sorts of other services that have been dumped into them, they are quite challenging areas to look into. They are predominantly around a foot high. So the vast majority of floor voids are somewhere in between 200 and 500 millimeters. That we're talking about 60% of floor voids. And we also see all sorts of other things in there, like moisture ingress, rising damp, animals, services, and so on. Now, when it comes to, one second. When it comes to services, obviously, when you see gas pipes and mains, water pipes, and so on, they need to be left as they are. But over the years, the floor voids really have been filled with all sorts of stuff. When you look at cabling and pipework, half of that is already disused. It's just been disconnected and abandoned there because it's easier not to do anything about it. And obviously, you've got networking, telephone, and TV, and HDMI, and all sorts of other cables. We just keep stuffing stuff into them, which creates an absolute maze of different building services. Now, we see a lot of defects when it comes to floor voids. We find woodworm. A lot of it is historic infestation. It's quite important to understand the difference between something that occurred 20 or 30 years ago, and we still see the evidence of that, versus something that is live and needs to be dealt with. We find high moisture, anything above 20% wood moisture content is considered dangerous and at risk of developing rot. Obviously, we find a lot of rot. That means timber has to be removed and replaced, whether that's dry rot or wet rot. We see a lot of evidence of that. Most of the time, this is a result of lack of ventilation of the floor void, and we see that quite a lot, whether brick vents are sprayed with expanding foam or taped over with duct tape, or blocked by vegetation or build-up of the ground around the house. We see a lot of blocked vents, and these generally translate into high humidity in the floor void. High humidity in the floor void translates into high wood moisture content. High wood moisture content translates into mold and rot. Now, a little bit of background when it comes to suspended timber floors. They've been introduced in the 18th century as an improvement over the floor covering sitting directly on the ground. And up until 1967, the ground underneath the suspended timber floor was completely open. It was just effectively a soil. The improvement allowed buildings to be built on uneven ground. It also allowed buildings to manage ground heave. We get a lot of that in the UK. And it was effectively timber mounted onto a solid external wall, ventilated underneath, with ground fully exposed. Obviously, important to note, the brickwork was highly hygroscopic. They weren't using engineering bricks until the 60s, so everything around the suspended timber floor is pretty much vapor and moisture open, and it needs to be managed accordingly. Now, when it comes to history, building regulations were introduced in the 60s, and in 1967, the requirement started of floor being below the suspended timber floor, being covered by concrete oversight. That was done to manage moisture, water, and evaporation from the ground below. Obviously, engineering brick was part of the requirement, and as I'll not mention later on, it was critical that engineering brickwork surrounding the floor void as well as the concrete that was covering the ground go together. Um, uh, Otherwise, we really pushing moisture from one area to another. Another requirement that was introduced was a continuous ventilation below suspended timber floor, and a continuous gap of about 150 millimeters to ensure that ventilation actually is effective. In 1995, the first introduction of the minimum U value entered building regulations when it comes to suspended timber floors, and the minimum U value was set at 1.2. It might be surprising that that occurred as late as 1995, but that's building regulations in the UK. What we currently see in floor voids is growing evidence of moisture ingress. We see a lot of standing water in floor voids. We see timber with condensation on it due to high humidity within the floor void, and obviously resultant mold and rot that follows. We see a lot more of that, and we also see that geographically concentrated in certain areas. It leads us to state that the buildings that have been built over the last 150 years are not fit for current climate and current conditions in the UK. One of the interesting notes is that when vast majority of construction occurred in the UK, both in sort of early 20th century and mid 20th century, we had a much drier ground. And the interesting reason for that is that we kept pumping a lot of water. UK was mining intensive country up until 70s and 80s. Mining activity relies on water being continuously pumped out of the mines to keep them dry. So obviously that lowered the water table around the areas where we had lots of mining happening. In 50s and 60s, we had a really intensive textile industry in the UK. At some stage, it was actually world leading textile manufacturing. Textiles are the most water intensive manufacturing process in the world, right? We used to pump a hell of a lot of water out of wells because mains water was way too expensive at that volume, and pumping water out of wells around the industrial areas, especially around the textile intensive industrial areas, again lowered the water table. Obviously, majority of construction during those periods happened around the areas where there was work, so where the mining was active or industry was active and lots of manufacturing was happening, we built lots of homes. Since we no longer mine and no longer have industry, especially around textiles, we've stopped pumping water out of the ground, and the water table came up a lot higher. On top of that, if you ask the Met Office, they will tell you that the rainfall in the UK has gone up by 40 to 60% over the last 10 years. As the air warms up, it can hold a lot more moisture, and obviously more moisture in the air means more intense rainfall. And we've seen even over the last couple of weeks, when it rains, it really does rain. We get localized flooding, partly because it rains more, partly because we just concreted over too much. So all of that leads to a higher water table in the UK. Higher water table leads to a lot more water coming into the voids. If you think about it, the floor voids are generally underground, right? If you enter the house, you might do one step or two steps. That's generally the height of the floor structure. The entire void is below the ground. Bear in mind, engineering brick was a recent introduction, so all of those floor voids are completely open to moisture. Water will just move through the hydroscopic brickwork like there's nothing. Obviously, the mortar is lime, again, letting water through. The ground is wide open, so whenever it rains, the water will just enter the void and sit there. And you can see on those pictures, not only standing water, lots of evidence of water coming through the walls because of the white sediment. And that means that a lot of homes are literally like indoor swimming pools, but without the appropriate infrastructure to manage that indoor humidity. So a little bit more on floor voids and issues they create. Well, number one is heat loss. You will lose up to a third of heat through uninsulated suspended timber floor. Now, that's quite a lot when you look at the total heat consumption of the building. Now, when it comes to moisture, we assumed so far that cooking, sleeping, breathing, washing, pets, plants, dishwashers, and everything else that we do indoors is the major source of humidity. This is based on building regulations. Building regulations treat indoor generated humidity as pollutant. But if you think about it, according to building regulations, all the buildings are built on engineering brick with concrete oversight over the ground below the suspended timber floor. Therefore, no moisture ingress happens through that route. Obviously, majority of our buildings were built before building regulations introduced that requirement, and therefore the assumptions from building regs do not apply to those buildings. And this is one thing that we really fail to take into account. We follow building regs that were designed for impermeable, right, waterproof, resistant buildings, applying them to buildings that are completely vapor open, that are water open in many cases from the ground, is not really that effective. On top of that, the recent research identified that we are actually basing our assumptions on indoor moisture generation on 1960s research, which, for example, included things like open-top washing machines. I'm not sure many of you have seen one. I used to have one at home, which was an open-top vertical spinning washing machine with a little hose on top of it that you needed to remember to put over your bathtub before it went into a spin. Otherwise, you'd have a nasty surprise. Obviously, the amount of moisture generated by that sort of clothes washing is 2 orders of magnitude higher than you get from modern washing machines at 1600 spin cycles, where you're effectively pulling out dry clothes. Now, there's been quite a lot of research into the realities of indoor moisture generation, and it's been found that we overestimate the amount of moisture we generate indoors by 2 to 5 times. Now, obviously, that means that the moisture is coming from somewhere else. Now, when you've got humidity, you will have damp and mold. These two actually go hand in hand. The problems we face when it comes to suspended timber floors is that we see them as highly humid environments. Some of the floor voids that we survey have 100% relative humidity. That leads to localized damp, mold, and rot. And because you've got a lot of infiltration that comes through suspended timber floors, in some cases more than half of total infiltration into the house goes through the floor void, you will get that mold, spores, and the humidity coming into the house through the floor void. So it's really important to see the floor voids as part of the house and really playing an active and dynamic role when it comes to indoor environment, which we quite often ignore. Just to give you ideas, apologies for bad pictures. This has been, my presentation was redone for this. We see the majority of moisture coming into the floor voids from the ground. This is based on 218 research done by Sophie Pulsemakers. It's a really good paper that looks at the moisture in the void and where it comes from. Number one source of moisture is the ground. Why we've got all that moisture coming into the floor void? Well, number one is we've built our homes on literally a swamp. It rains in this country, and there is absolutely no barrier between the floor void and the outside environment. And obviously our floor voids are drier and warmer than outside. First of all, it doesn't rain there. Well, that means it's drier whenever it rains. Secondly, they are warmer. You've got building services, you've got, there's a shielding around that, so there's no wind blowing through it. It's not exactly open to the environment. On average, floor voids are about 10 degrees warmer in winter than the outside. And obviously, when you've got something which is warmer, the evaporation happens at a much higher rate. Those floor voids evaporate, the water evaporates from the ground into the floor void, permeates into the house. And as the water evaporates into the floor void, it means the ground becomes dry underneath it. That process automatically pulls the water from the outside. Bear in mind, footings of most homes in the UK are very shallow. They're not even a foot deep. That means you're completely open to the environment. As the ground around you gets wetter, the moisture will follow to the drier side of it, naturally going for equilibrium. As the moisture enters the void, it will evaporate and then it will infiltrate into the house with the incoming air. And obviously, not only that generates high humidity in the floor void, that will also increase humidity in the house. Other sources of moisture in the floor voids, defective drains, defective rainwater goods, possibly leaks from the inside. We've seen a lot of properties where defective roofs caused a lot of water in the floor void that wasn't being detected within the house. We did a number of jobs for Nottingham City Homes. At one stage, we found 30 properties of the same archetype being flooded within floor voids, and we identified that there was a hip end coming onto the chimney stack with the flashing that was defective. The mortar within brickwork was already washed away. The water was entering the chimney cavity. It was coming down through 2 floors on the chimney cavity, hitting the hearth, and then getting that hearth completely wet. The timbers that were socketed into the fireplace hearth were obviously soaked. That was obviously a defect. These properties were scheduled for retrofitting, and if we hadn't looked into the floor void, nobody would pick up that defect, right? So it's really, really important that floor voids are inspected and all the potential issues are recognized before we embark on any retrofit, so we avoid locking in problems for the future. Now, we talked about earlier on high humidity leading to high wood moisture content. How does this work? Well, technically speaking, timber and the surrounding environment will always tend to be at equilibrium, right? And if you look at this wood sorption curve on the right-hand side, it shows you the equilibrium between timber and the surrounding air. When relative humidity surrounding timber reaches 75%, that timber will be around 16-17% of water, so wood moisture content around 16-17. When the surrounding air reaches around 80 or 85%, the timber will be above 20% wood moisture content. Now, at that point, you've got exponential growth in wood moisture content versus every increase in relative humidity. Timber becomes more and more saturated as the humidity around it increases. Now, this is really key because we know that anything above 20% of wood moisture content risks rot developing within that timber. Obviously, it's not like it hit 20%, tomorrow we've got rot. It happens over months, but once rot sets in, if the moisture content and the relative humidity maintain at high level, we will have structural failure within months or maybe a few years. Again, it's really critical to recognize those potential issues when we're attempting retrofitting of properties, because if we don't recognize that as a risk, we might be exasperating that risk doing various measures or doing inappropriate measures. It is really critical that we see that. Now, when I talk about relative humidity, obviously the best for humans is something between 40 and 60%, as you can see on the left-hand side. Anything lower than 40, it becomes uncomfortable. Your eyes will start itching. You'll start coughing. Your throat will get dry, and so on. Anything above 60, you again become uncomfortable. Your sweating doesn't work anymore. You can't really regulate temperature. It becomes a little bit like being inside a greenhouse or something. Now, what we see within floor voids is that almost all the floor voids we survey are to the far right of 60%. Again, the ideal environment to grow bacteria, viruses, fungi, dust mites, and other nasties is in that high humidity space. And this is what we see with almost every single floor void we survey. So it's really critical to understand the potential issues that this can generate and to understand the potential solutions as well. Let me just jump over the next slide. Okay, now what other things enter floor voids that we really don't want? And this is again based on quite a lot of research. We have obviously up to 54% of infiltration coming through the floor void. That air carries humidity, bacteria, contaminants, and mold spores. I mean, mold spores, let's focus on those a little bit. We all know that damp and mold carries risk to health. Now, different people have different levels of susceptibility. Some might not be impacted at all, others might develop terminal illness from the same amount of mold spore exposure. And because of that, no amount of mold is assumed to be safe, right? Any mold can be dangerous to the inhabitants. Well, now imagine that you can't see the mold, that the mold is hidden beneath the floor, but you are still exposed to mold spores that freely come into your house through infiltration from that floor void. If you don't see the mold, you can't combat it, you can't deal with it. And yet you might have people exposed to that for years without your or their knowledge. This is a risk that needs to be really taken into account. On top of that, you've got microbial volatile organic compounds that come through. And generally speaking, that's based on the ground level. Because the ground is wet, you will have all sorts of microbes growing there. And we found a lot of VOCs being emitted from that ground. Again, that comes into the house through infiltration. And again, it is something that needs to be taken into account. One last thing before we jump off, radon. There might be a slide on that later on, but it's important to understand that 1,100 people die from radon exposure per year in the UK. That is more than we have deaths from car accidents, right? And yet, when it comes to road safety, we've got regulations, we've got signs, we've got speed limits, we've got humps, we've got all sorts of things trying to control that environment. When it comes to a similar amount of deaths that we've got from radon exposure, there is very little attention paid to that. Again, radon enters homes through the ground into the floor void, and then through that floor void into the house, right? This is how, in almost every case, we get radon coming in. The properties that are built on solid concrete floors are not effective. Properties are not effective from the outside air. The moment radon sips into the atmosphere, it's immediately diluted. But when it sips into the house from the ground, it then enters the house. Now, another thing that you need to take into account when retrofitting, making the house airtight and not dealing with the floor increases the risk of radon exposure and therefore increases the risk to occupant health. These things really need to be taken into account when we're dealing with retrofit design. Now, you might say, okay, well, we just add ventilation to the property and that will solve the problem, right? Well, unfortunately, that is wrong. And again, there's been a lot of research that looked at properties with negative pressure indoors, whether you're using continuous extract ventilation or passive stack ventilation. And in almost all cases, adding ventilation to a house that has untreated floor void will increase the amount of air that comes from that floor void. Now, when you insulate the property and you make the property airtight and not deal with the floor void, you will actually increase the amount of air that comes through the floor void, carrying excess humidity, carrying potentially radon gas, carrying mold spores, microbial VOCs, and other things. So again, care needs to be taken when we designing retrofits to ensure that we're not making the situation worse. There's been a lot of research showing increased humidity indoors when we just add extract ventilation because there is an increased infiltration from the ground below. So that's again something that you need to take into account when designing retrofits. Obviously, people have tried to deal with those problems. In the US, the most common way to deal with mold or wet and moldy crawl spaces is to fully condition the crawl space. Normally, the perimeter walls would be insulated. You would fully cover the ground, and then you would also ventilate that ground uh, to the outside of the building to make sure that the humidity that's building up in there, or moisture that's building up in there, can be evacuated to the outside of the house. Now, bear in mind that these homes are built on concrete blocks, right? All the footings are actually water impermeable, and that's an important part to take into account. We've also seen increasing trend in the UK to remove suspended timber floors and replace them with concrete. And to be honest with you, I've done this myself probably 20 some years ago, and I've seen the negative consequences of it. Just to give you an example, I was doing a retrofit in Twickenham, London. We removed suspended timber floors. There was half a meter of floor width below that. We backfilled that with MOT, compacted that, did initial screed. I put 200 millimeters of rigid board PU foam. We put DPM below and above that, and then we wrap that DPM into under skirtings to make sure that we fully isolate it. We had rising damp before we got off site. Just by the time we finished decorating the place, we started seeing that sort of ribbon of black mold appearing all above the skirtings. At that point, I couldn't really work out what we did wrong. We put double DPM. We had building control officers come in, have a look at it. Everybody proved that it was great. One thing we didn't take into account, and this is where the current building regulations thinking is literally inapplicable to 120-year-old properties. Building regulations assume this is fine because building regulations assume that the perimeter walls are built from engineering brick, which is waterproof and impermeable. Unfortunately, our existing homes are not built like that. What happened in that particular case, the moisture didn't go away. It just found a different route to evaporate from the ground. And in that case, the walls, which are fully hydroscopic, London stock brickwork, fully vapor open, the water just permeated upwards to the nearest warmest point, which happened to be indoors above the skirtings. That is a key issue because these walls now become wet, almost saturated in places. In winter, you've got risk of spalling, brick damage, mortar being eroded. Wet brickwork for substantial amount of time becomes brittle. You're starting to impact on structural integrity. Now, there was a really interesting paper in Rick's journal that came out about 10 years ago, stating that properties, replacing suspended timber floors with concrete is a defect that needs to be rectified. It's a defect that puts the entire building in danger, and it needs to be rectified by reinstating suspended timber floor and reinstating the ventilation underneath that suspended timber floor. And I'll add a little bit more to that. So again, we've tried dealing with these things in the UK. Obviously, it's not particularly possible to do a full crawl space conditioning with full sort of tanking, mainly because they're about foot high. You can't work in those spaces, and B, every 4 to 6 foot you've got sleeper walls. Again, it's impossible to have a continuous barrier on the ground, so it's not particularly applicable. So how about insulating, right? Well, number of things have been tried. So you could try to introduce a barrier at the floor level as opposed to introducing barrier at ground level. Obviously, doing that from above is incredibly disruptive. If you think about insulating floors from above, you need to remove furniture, carpets, underlay, carpet grippers, floorboards, and then you're kind of trying to literally put a square peg through a round hole. These floor joists that have been there for 120 years are not really parallel. They're not perfect. They warped all over the place. They wobbly. Having a perfect fit of insulation between those floor joists is near impossible. Keeping that insulation suspended there is quite a lot of work. And at the end, it's not particularly effective. You'll get a lot of thermal bridging. You'll get a lot of thermal bypass around the gaps. Even if you have, polythene or something on top of it for air tightness, you still can't combat the thermal bypass that gets right against it. It costs an absolute fortune because you have to decant the tenants somewhere else. And at the same time, when you're pulling the floorboards off, quite often you end up having to pull the skirtings off. When you're pulling the skirtings off, they come with a chunk of plaster. Not really a sustainable way forward. generates a ton of waste. And obviously the carpets could have been there for another 10 years. Having to replace the carpets is the opposite of sustainability. So not really a great approach. Now, there's also been a lot of talk about the need to put vapor open insulation within the floor, because vapor open seems like the right way forward, and the same approach being adapted to loft insulation, vapor open, or to the roof insulation, vapor open is better. Unfortunately, that is a complete fallacy. When it comes to loft insulation, there's a very good work that was published in March this year by Health and Safety Executive, stating that vapor open roof insulation is a much higher risk because it allows moisture in a way of water vapor, but at the same time you can't really ventilate it out. Floors are no different. There will always be positive vapor pressure from the floor void. Floor voids are naturally a lot more humid and contain a lot more water. Also, these are the environments that are not that well controlled. We don't have heating there. We don't really have mechanical ventilation. These environments are unpredictable and generally very wet. Now, if you insulate in between the timber joists with vapor open insulation, you're still allowing all that water vapor from the void into the timber. But you've made one important change. You're now preventing any ventilation from carrying away any of that moisture, right? The timber is now fully enclosed in insulation that lets moisture through, but doesn't enable ventilation to take it out. So, and again, with insulation between timber joists, that timber gets wetter and wetter and colder as it goes towards the bottom. So right at the bottom of the timber, you're actually putting it now into the interstitial condensation space. So that water vapor will effectively condense into water. That water will then create an ideal environment for damp, mold, and rot to develop. Again, not the right way forward when you have colder, wetter environment below. Now, there's been quite a lot of work done in the US when it comes to trying to work out the appropriate ways of insulating suspended timber floors. And this is a slide from a Building Research Institute from US, which effectively states that because there's always positive vapor pressure from the void, and there's always a drier and more controlled environment within the house, isolating the timber floor from the void, in this case from the crawl space, is the best possible approach. You need to both insulate it and create a vapor barrier. And in this case, the ideal approach would be to install a rigid insulation below the floor joists with all the joint, with foil on both sides. Aluminium foil is obviously vapor impermeable, but not just aluminium foil on both sides, aluminium tape on all the joints, and also aluminium tape over every single screw to make sure that there is actually no vapor penetration. If you do that, you end up with your timber floor in a warmer, drier, and ventilated environment, which is obviously critical to maintaining its longevity. Obviously, when you think about floors in the UK, which are, the voids are foot deep, not really something you can operate in. Sleeper walls every 4 to 6 feet. Again, even just getting a rigid insulation underneath that floor is a challenge. Fixing it from below is near enough impossible. So if you look at the far right, closed cell spray foam is seen as the second best choice when you've got floors that you really can't get underneath. So if you've got a basement or something which is near enough big as a basement, you've got the luxury of actually working below it. You can easily fit insulation, you can make it airtight and vapor tight, and on top of that you can put, let's say, a concrete sheet or double plasterboard to also make it fireproof. Brilliant. In floor voids that are 1 foot or around 1 foot, literally the only thing you can do is apply closed cell spray foam. Closed cell spray foam is called semi vapor impermeable, and if you look at building regulations, anything thicker than 1 inch of it is seen as an effective vapor barrier. Therefore, if you apply closed cell spray foam over not just the floor but the joists, minimum of 25 millimeters, you're actually isolating those joists from the floor void, both thermally and moisture wise. And this is probably the only thing that we could effectively do in the UK. So when it comes to indoor environment impact, we've obviously been insulating floors for some time. Over the last 10 years, we've insulated around 5,000 homes in the UK, and we've been collecting data from a lot of those. And quite a long time ago, about 8 years ago, when we were doing, I think, the 50 properties for Camden Council, we were working with National Energy Action to look at the impact of insulation on indoor environment, but predominantly indoor air quality and the occupant health and so on. And part of that study was to look at humidity impact of insulation. And since I've been working in retrofitting for best part of 30 years, the default assumption is that any energy efficiency measure applied to a house will increase its relative humidity, because we're actually reducing ventilation, we're reducing the amount of air exchanges between inside and outside. Therefore, the humidity will increase because the humidity comes from inside the occupied space. Imagine our surprise when we did the research and we looked at about 15 properties, and in every single case, after introducing, without changing ventilation, after introducing floor insulation, and again, closed cell foam, fully airtight, vapor tight, and insulative material below the floor, in every single case, we saw relative humidity in a house drop. Obviously, this goes pretty much against your typical accepted retrofit knowledge. When you insulate, you have to ventilate, because obviously you're increasing the humidity and so on. In every case where we insulated the floor, humidity dropped, and dropped substantially. We're talking about 3 to 9 percentage points, right? So in this particular case, we're looking at, 62 to 66 percent of relative humidity before the job, dropping down to 51 to 54 after the job. It's a significant increase. Suddenly, we're moving the relative humidity from that unwelcome, too high, risk of damp and mold band above 60 to almost bang in the middle of that ideal relative humidity band, between 40 and 50. So that was the first surprise, which was like, okay, what happened? Was the moisture coming from somewhere else that we've just stopped coming into the house? Really weird. But even more surprising was the fact that the humidity in the void, which started at almost 100%, post-installation dropped to 80. Now, at this point, this is really counterintuitive, because the assumption is that as temperature drops, relative humidity increases, all other factors remaining equal. And this is what happens when you insulate the floor. Suspended timber floors, or the voids below suspended timber floors, are somewhere in between 14 and 18 degrees in general before you insulate. After you insulate, they end up somewhere between 10 and 15 degrees. So there is about 3 to 4 degrees temperature drop within the floor void. Obviously, insulation is a big impact, but you're insulating the floor. You still have thermal bridges when it comes to structural walls. You've got building services. Even though you insulate some of them, it still gets in. And on top of that, floor voids are not outside environment. They isolated from the outside environment. Even when they are ventilated, they're quite shielded, so they would be naturally warmer. Now, why on earth did relative humidity in the floor void drop 20%? We didn't know at the time. Earlier this year, I found a really interesting research paper, which is referenced in the original CPD, that states that for every point increase in temperature within the floor void, evaporation within that floor void will increase exponentially, which means that the cooler the floor void, the lower the humidity within the floor void, because the evaporation is dramatically reduced. Now, when you think about it, when the evaporation within the floor void is reduced, the whole movement of moisture into the floor void is reduced too. So by insulating, and this is one of the unintended consequences, which turn out to be quite positive, by insulating the floor and completely isolating the floor from the floor void, you're reducing the evaporation into that floor void, because you've reduced the temperature into that floor void, and as you reduce the evaporation of that floor void, the relative humidity is reduced as well, and therefore the risk to building fabric is significantly reduced. Now, we went back about a year later to check humidity readings again, and we've witnessed that for the same time period in August, we saw the same reduction in relative humidity indoors maintained over a prolonged period of time. Again, that means that there are some measures that actually reduce relative humidity indoors, and that is maintained. Now, when we look at energy savings, that's another thing that's really worth considering. We're obviously talking about various ways of insulating floors. Let's just look at insulating floors. You could do it by ripping it up, putting some sort of insulation between the floor joist, devising some methods to hold it in place, whether that's a net or timber slats or anything else that you put in there, and you could put everything back together. Incredibly wasteful, very unsustainable, because you destroy a lot of stuff that's there already. You've still got a lot of waste because obviously after cutting those rigid boards between joists, there are lots of offcuts. You can't just throw them in there randomly. But more importantly, you literally are not saving energy, right? There's been a really interesting deep study done by Leeds Beckett University. The results should come out as a big report shortly, but I've seen presentations from Professor David Glue on that front. They've looked at 6 floors insulated using traditional methods, which means do it by hand from above, destroy everything. Half of those floors generated no measurable energy savings, literally no measurable energy savings. Now, the other half of those jobs generated energy savings below 5%. In all cases they've looked at, the energy savings were actually lower than the ones modeled in RD-SAP. On the other hand, Leeds Beckett did a co-heating test on a house which had floor insulated using closed cell spray foam applied from below. They published that in a paper in 2019. They found 24% energy savings based on just insulating the floor, right? Now, what happened was that not only you insulating the floor with 5 inches of the best performing insulation system that you can actually apply, you also made the property airtight. Insulating the floor with closed cell spray foam from below reduced or improved the airtightness of that house by about 40%. So you get 40% airtightness improvement, and then you've got significant U value improvement down to about 0.18, right? Combined, those two delivered 24% savings, okay? At the same time, you didn't have to move out the furniture, you didn't have to rip up the carpets, you didn't have to rip up the floorboards, you didn't have to do any making good afterwards. The whole insulation was done in a day almost without any disruption within the house. So that's quite important because it's A, convenient, B, impactful, and C, sustainable. You've retained everything that was in the house, you didn't disrupt anything, and you achieved significant energy savings. Whereas the distractive, unsustainable process doesn't really generate much. Now, on that point, I would like to note that if you just do a SAP model or RD-SAP model, whether you've done the job right and you've generated 34% energy savings, or you've done, or you just put some rock wool in between and you generated, 4% savings, or you just said that you've done it, but you haven't really done it because nobody can check, it's underneath the floor, you get around 2 points improvement on EPC. It completely doesn't matter from a perspective of EPC what you do to the floor. But actually in practice, when you look at energy savings, it matters a hell of a lot. And it actually spills out into other measures. We've got one of our partner installers, Concept. They install heat pump day in and day out. They also have 4 vans installing a cupboard floor insulation. What they've noticed when they do energy consumption monitoring on all the heat pumps is that where they installed floor insulation with the heat pump, they see 30% drop in energy consumption from that heat pump, right? That was based on 70 homes that they monitored. We're now looking at 200 homes following year, and we're looking at around 25% reduction in electricity consumption from the heat pump. Now, that not just means that people pay lower bills, literally lower bills. In some cases, that's the difference between people paying lower bills or paying the same bills because of the electricity cost being much higher than gas. But it also means that if you combine certain measures well, like let's say heat pump with floor insulation, which is a really high impact measure, especially on air tightness, you can install a smaller heat pump, which saves money. You might not have to upgrade electricity supply to the house, which saves money, in some cases thousands of pounds when you have to dig up the road and run three-phase power supply. You might not have to change the radiators in a house because the heat loss is much lower. So even with lower temperature heat pump, that emitter can be good. And you might not have to insulate pipework because that is done with insulation at the same time. In some cases, combining heat pumps with really effective floor insulation, in this case, closed cell spray foam by Cubot, can reduce the overall cost below the cost of installing a heat pump on its own. So that's something that's worth considering. And unlike RD SAP, these savings can be calculated using either MCS or CIBSE software for heat pump installation, because you actually input U values and air tightness for each area independently, and I can tell you, keep that radiator, it's good. So when we're looking at impermeable, vapor closed insulation, we really see a big difference when it comes to when compared to other installations, but also, it's the right way to do it when you compare that against the loft installation, for example. People have had concerns about generally spray foam loft insulation, and it's understandable. Let's just focus on one key difference between the two. When you apply insulation below the suspended timber floor, you're insulating that floor from the outside. Literally, the timber now sits on the inside of the insulated envelope, which is dry, which is ventilated. You can control that ventilation and so on. And at the same time, you're protecting it from the cold, wet outside. When you spray foam insulate the loft from the inside, you're literally putting all the timber into outside of the thermal envelope, right into the interstitial condensation risk, and exposed to the outside. So suddenly the timber is in a colder area with all the risk of condensation. And then if you don't ventilate that timber appropriately, if you don't prevent from moisture from getting into that timber by either using closed cell or having a fallback plasterboard on top of that or both, then obviously you'll have issues. And we've seen that happen again and again. It doesn't mean anything about the actual measure. It's all about the quality of the installation, not following the process, not actually following building regulations, and doing the job badly. So that's something that's worth bearing in mind. I think we might just do one more item and then get into questions. So I talked a lot about ventilating floor voids, and it is incredibly critical to do that for a number of reasons. First of all, moisture enters floor voids from the ground. That's how it gets in there. In a lot of cases, we see standing water in there. This will increase the relative humidity inside the floor void, and it will impact the timber, it will impact the walls, it will impact on the ability of walls to dissipate moisture as well. Bear in mind, there's one critical fact when it comes to traditional solid brick walls. They are vapor open and they're hygroscopic. That means water freely enters them and will just rise up to the nearest point where it can evaporate. And if you think about the external features of what happens below the damp-proof course on solid walls, quite often you will see a render detail, which effectively covers the wall from the outside all the way to the DPC. That render details means that the moisture that enters that wall and creeps up doesn't have any way of evaporating to the outside environment. At the same time, that solid wall will be exposed to the floor void for up to about half a meter, right? It's exposed to the floor void. If that floor void is not ventilated, then again, we're removing any capability of that wall to evaporate that moisture and for that moisture to dissipate to the outside environment. It will therefore become wetter. And as that wall becomes wetter, higher and higher up, it's more conductive. And as it's more conductive, you lose more heat, and at the same time you've got risk of rising damp indoors. So you've got all sorts of consequences that can actually happen just because you've ignored obvious and critical things such as floor ventilation. And there's been quite a lot of research done recently, and there's a paper from 2018 where researchers have gone back to properties that had brick vents closed to try to save energy, and they found that average relative humidity in those voids was between 90 and 95%. At that point, you enter a really high risk for timber rot, but you also enter really high risk for the walls, for the solid walls all around the property to become wetter and wetter because they just can't dissipate moisture. I think at this point, and this is the slide on radon, but I've already touched on that. I think at this point we might as well open it to questions.